in my thermal underwear thermal clothes that I put my mine clothes over it. So very nice to have Paul join us. He's been on a few of our workshops with us, and will be joining us as a member of the GCC, and is always full of creative thoughts and fun, interesting, and we hope sometimes useful, Paul, ideas. Managed to find application in many areas. Mining's just one of them. Had a long-term project with Rob Morrison at the JKMRC, which I think is maybe our first call, at least 15, 18 years ago. And has really contributed a lot around insights you can get from looking at particle and fluid motion, particle contact, particle fracture, within really complex systems that we're still trying to understand, which makes them the most interesting ones, of course, the ones that are difficult to understand. So looking forward to Paul, who's with Saro, updating us with some of his new and interesting ideas, which he always does when he presents. He always brings the freshest, most interesting stuff to the audience. So over to you, Paul.
Well, thank you very much. I have to start with a comment for Magnus, who looked like he was trying to rotate his camera into the opposite position. So I think he was trying to make us in the Southern Hemisphere feel comfortable.
Might have been.
Okay,
sorry for that. I was changing between my computer and my phone.
No, that's all right. It just looked like you wanted to be in the Southern Hemisphere with us.
Yeah. I panicked. I didn't want to have the sound, echoing.
Anyway, Malcolm, thanks for the introduction. And I have to say, I didn't really need to have quite so much detail about your pajamas, but good to know you're warm. Okay, let me start then. So the title I've sort of opted for was Particle Scale Modeling of Comminution Processes. A question for whoever's chairing is, do you want to take questions as we go through, or have people wait till the end and then run out of time?
They will wait for the end.
Yep, okay. Okay, so start with just acknowledging contributions from people and some collaborators. So core people from our group who've worked on this for a long time, Matt Sinnott and Sharon Cummins, and then Gary Delaney, who's worked on the 3D particle breakage, Nick Stokes for a long time, David Thomas, who's our lead software engineer, the Cicero Workspace software team, as Malcolm mentioned, Rob Morrison. So I think, Malcolm, it's 22 years now, maybe 23, but who's counting? And then I'll show you a few things from our digital human work. So that is in conjunction with Simon Harrison and Ray Callan. A little bit of an outline of what I'll talk about. So introduction to the particle methods. So for us, that's DEM and SPH. DEM, I expect everybody knows, is very familiar with. SPH, maybe yes, maybe no. I'll show some application examples so that you get a reasonable idea of the breadth of what we do and the sorts of applications that we've been looking at various stages. Then I'll talk in a bit more detail about breakage in DEM, and then I'll focus on a couple of crusher models, and then I'll talk about the complete SAG mill model, which is becoming a very, very complex model with a lot of moving pieces. Okay, so the particle or the computational methods we use, DEM and SPH, so they provide a way of looking deep inside the equipment and sort of understanding, getting data, getting information on things that you can't really measure or see traditionally. So the DEM method, I think everybody should be familiar with. So you're basically just tracking a whole lot of particles with different sizes and shapes, predicting the interactions with the environment and the collisions between the particles. So it's a method to track particles and collisions is the principle of physics. The SPH method is a continuum method, but it's a meshless Lagrangian continuum method. We actually use it in several different ways. And in particular, we are using it for modeling fluids, but also we use it to model solids and first principle fracture of solids and elastoplastic solids. But basically, it's a continuum method and you're solving PDEs. And so if you can write down a normal PDE, or if you can solve it with finite element methods, you can use it in the SPH method. And that then gives you the advantages of being able to track complex free surfaces at no cost and be able to follow complex multiple materials. So this is a sort of a rough method sort of phase diagram trying to explain sort of how our methods fit together for what we do. So we're using DEM for the collisional dominated interactions for breakage, segregation, cohesion. At the bottom we've got SPH for fluids, elastic solids, elastoplastic solids, elastic little solids, membranes, phase change, thermodynamics. And we're often coupling the DEM and SPH method together in different ways. We also use some traditional grid-based methods. We use finite element methods for some things, particularly structure deformation. And we use finite difference methods for modeling sort of gas flows, particularly coupled to the particle methods for the particles. The BOIM is biomechanical models, and I'll just show you a couple of those. And that's essentially what we use for modeling humans or parts of humans. Sort of over on the side, we use a little bit of Lattice-Boltzmann methods as well for permeability measurement, but also for mainstream fluid mechanics. So Comminution sort of sits across several of these methods, but predominantly uses DEM with SPH, and sometimes with a little bit of finite difference if we need some airflow in there. The human environment stuff, I'll show you a few examples of that. That then covers the areas right. We work in lots of other areas, but I won't show those on the diagram. Okay, so here's a very simple SPH simulation. So this is just pouring glass into a milk. Sorry, milk into a glass. It would be very interesting to see the other one. So what we've got here is a free surface liquid coming from an inflow. It comes into the glass, it hits the wall, it spreads out. It becomes very thin and undergoes a ligamentary instability, which then causes it to break up. And when it gets to the bottom, it starts to flow across the bottom, and you get collisions between different parts of the flow, and you get ejection fluid in the free surface and splashing. Many of you will have seen this one before. It's a common one I use to sort of try and show SPH for somebody who's not familiar with the method. See the complex free surface behavior. You can see the waves breaking. You can see collisions. But SPH is a method that's very, very well suited for complex free surface flows. It's also very friendly for coupling to I'll show a dam collapse now. This is the St. Francis Dam in California, but it's relevant in the mining industry is mostly with tailings dams. So for people who want to wonder what happens if the tailing dam collapses, which of course from time to time unfortunately happens. These types of methods to predict the subsequent inundation pattern, the degree of flooding, how long it takes for the flood waters to get to various locations. Similar sort of disaster type way. This is an open pit mine where you're then interested in slope stability, and if the slope collapses, you're interested in where that material goes to. So this is a section of an open pit that's fragmented. The majority of the rock, even though it's fractured, is still relatively stable and sits at a relatively high angle of repose. But that mobilized rock that has flowed is still sufficient to flow significantly along the sides here to fill a reasonable fraction of the side of the open pit, and obviously will destroy any infrastructure and kill anybody that gets in between. So this is an area that we occasionally work in as well. It's sort of related to mining here. Okay, so quick quick overview across a whole range of different areas here. I won't talk about any of these in much detail. So the first one is separation. So lots of different types of machines to separate. So at the top here we have a simple example of a small section of a vibrating screen. Spherical particles on the left and non-spherical on the right. So I'll set them running. Bottom left we've got a double deck banana screen. And then on the bottom right is the banana screen, and have a modest level of cohesion. You only need a small amount of cohesion, say interstitial fluid, to completely block the banana screen up. You'll see here that the spherical particles peg the holes very well. They can get very different behavior. So shape is critically important in separation flows. In fact, in all the gradient flows we're interested in, the particle shape is critically important, and you always need to include that. We've got a bunch of crushers. So we've got gyratory, primary gyratory, cone crusher, horizontal shaft impactor, various roll crushers, hammer mills, shaft impactor, double roll crusher, roll crusher. I'll show you a couple of these later, so I won't show you them now. Then we're interested in obviously coarse grinding. So we've got sag mills, HPGR, vertical roller mill, various roller tumbling mills, rod mill. I come to the sag mill model, we'll talk more about that there. But also fine grinding, so towel mills, iso mills, mills, lots of those as well. So we use the models across the board spectrum of comminution process. We're also interested in mixing, sometimes mixing in the comminution device, but often in manufacturing processes. So this one's a four-blade plowshare mixer. We've got a whole range of other machines there. So we're interested in the nature of the mixing process and the quality of the mixing. Does it fully mix, and to what degree are the dead zones and unmixed regions? So it's actually not a good mixer at all. It's not particularly good, but you can see inside and see what they're doing. Storage and transfer of bulk materials, so all sorts of poppers and containment devices, transfer chutes. So this is transferring between one conveyor up here for a very complex inverted chute onto another dump below. Here we have a hopper where once you include the particle shape, you can directly predict backholing as emergent behavior without having to rigging the DVM model to try and force it to produce shape. Again, very, very important in all these applications. Now, this is just the first of the examples I'll show you for the digital human model. So these are basically where we have a human introduced into fluids or solids. In this case, it's actually Olympic swimming. So this is a real Olympic swimmer. We've got a very accurate laser scan of their body, and we've got multi-camera video of their swimming technique. So then we digitize the motion, and then we can impose the motion on the swimmer. Now, mathematical structures we use here are the same for the mills as we are for, say, the swimmer. So the framework's very versatile, which can range from humans to sort of type of machine. Once you've got the digital model of the human, then you put them into the SPH virtual water, and the virtual athlete then produces the motion that we've digitized, and that creates drag and lift in the water. And the motion here of the swimmer is a direct prediction of the kinematics that the swimmer is using in the model to produce motion. Also look at things like platform diving. So this is again an Olympic athlete doing a inward 3.5 somersault dive. Complex biomechanics followed by body doing complicated things, interacting with the water. The last of the general examples I'll show is additive manufacturing. So this is a particle bed. In this case, it's titanium grains, which are about 20 microns. got a laser. In this case, the laser is rendered as purple, so you can see where the laser heat source is. The laser deposits heat on the surfaces in proportion to the view factor of the grains. The grains are modeled as SPH clusters of particles, and that means that we have both the discrete nature of the grains, but we also have the continual model within the grains, which allows us to predict the internal convection or conduction and melting of those grains. And then once they're liquid, got a transition from a sort of granular system to locally to a liquid system. The liquid flows under pressure from the laser and sort of forms a solid. So I'll play that, we'll see how it works. You'll see the lasers moving on. The colours showing the viscosity, which is red for free flowing, and the other colours as it solidifies. The dark grey shows you the material that's really solidified. So you can see the dark grey is what the particles are all sort of smeared and merged to get to the original grains. The way this process works is you lay down a layer of beads, you do this process, then you put another layer of grains on top of those, and then you do it again and build up the layers progressively. So this model is a sort of a hybrid DEM SPH model. It's got DEM components because it's dealing with grains that are stuck together, but because we want to do the internal heat transfer, the solidification and the melting, and then solidification again. We've got all the SPH continual parts provide us okay, so talk about breakage, rock breakage modeling in DEM, at least the way we do it. So this is the basic elements of it without too much detail. So for compressive breakage, we're using an elastic threshold strain energy. And for impact breakage, we're using the damage energy or incremental damage, which is the energy in a collision that's above an elastic threshold, which everyone tends to call E naught. So in the impact case, we're measuring the accumulating damage energy. In the compression breakage case, we're looking at the elastic strain into particle contacts. And those give you the information about when a particle should break. Once a particle is broken, then what we do is we replace the fracturing parent with an appropriate assembly of daughter particles, all of which are non-spherical. They're packed into the space that was originally occupied by the parent. Progeny size distribution essentially comes from the more recent updated version of the T10 model, so basically driven by drop rate or breakage test data, but including size effects. So we have an extra parameter in on top of the traditional ones that takes into account the size dependence of the material characteristics. So once you've got the progeny distribution from the T10 progeny model, we basically put very small versions of these into the big particle, then we grow them, allow them to rearrange until we've got a very dense packing that fills the original parent's size or shape and volume, but with progeny whose size distribution matches that which came from the. And we do that for every single breakage event that occurs in either the crusher or the hill. In some of these machines, you can be looking up to sort of breakage events per second. So you're doing very, very large numbers of these breakage replacement. Just to show you how it works, this is an example of two relatively equal-sized particles colliding at a high speed. There's 100 millimeter particles, and resolve down to 1 micron. Oops. And you can see the replacement models that occurred instantaneously. The progeny are then free to move, conserves energy, so the original energy that remains above the energy dissipated by the elastic part of the fusion that remains energy inherited by the progenies allow move into each other and spread out with that energy. Here's a similar type of particle hitting a solid surface. And like you've got the size distribution of progeny. So this is essentially what happens in an impact crusher. So I'm going to talk about the size reduction mechanisms that we're using now in the DEM model. We've got 5 of those, depending on how you count them. So traditional single impact body breakage is mechanism 1. Mechanism 2 is the incremental damage theory, which essentially is body breakage as a consequence of the accumulating damage from the energy above the elastic threshold that it accumulates. So essentially each time you have a collision, there is a probability of breakage that depends on how much damage has occurred. Then if it breaks, then the accumulated damage energy then determines the breakage event, which controls the size distribution of the project. We've got 3 surface loss mechanisms. The first one we call chipping. And so this is for an angular particle, the preferential loss of corners and edges due to impact. So if you have a particle with a sharp edge and you hit it, say 45 degrees near that edge, you can actually shear off a whole large piece of it. So you don't necessarily need a lot of energy input, but you can remove quite a bit of mass from it, and its impact is to round the particle by removing the shoulder, the corners and edges quickly. So chipping is a more efficient mechanism, but it'll lead to a rounded particle, and at that point the chipping slows down and eventually won't occur. Similarly, rounding, which is frictional sliding around those corners and edges, so it's a preferential loss of those corners and edges and asperities due to sliding contacts. And the last mechanism is the traditional abrasion, so that's essentially frictional rubbing against the particle that causes a volumetric radial loss, so the particle basically shrinks radially. So chipping and rounding have a significant effect on the particle shape. Abrasion predominantly affects the size of the particle. These connect together in an interesting way, particularly for a SAG mill. And this down the bottom is a diagram indicating what we currently think of as the life cycle for a large rock in a mill, particularly a SAG mill. And so you've got your particle here. And so the key question is, given its size, are the collision energy spectra that mill generates, do they have any collisions that are large enough that when you subtract off the elastic threshold that you can actually do damage to the particle? Typically for very large rocks, the answer is no, the rock is too big, and the energy that the mill can provide when you divide it by the mass, that ratio of energy provided by the mill to the rock mass is always smaller than the ingot, so you can't do damage to it and you can't do body breakage. If that's the case, then the only mechanisms you have available are the surface mass loss mechanisms. So most particles start off very angular, so you start with a rounding phase where you use the chipping and rounding to take the particle from an angular particle to a round particle. Once it's relatively round, then your only remaining mechanism is abrasion, and that then just wears away the particle. And this is the origin of your critical sizes for rocks in a SAG mill. These are ones that are too big to break yet, but they haven't got small enough to get into the breakage range. So the only thing left is to just slowly abrade the surfaces away. They shrink, and as they shrink, then the collision energies that the mill can provide, they remain constant, but as the M decreases, eventually the E on M exceeds the E naught, and you can start to accumulate damage, and at that point you start to have a chance to break, and the smaller it gets, the more damage accumulates, and the faster it accumulates, and eventually you'll end up with a body breakage event. That body breakage event will then create angular particles, and then you go back, and those of course, progeny particles do the same thing. If they're large enough, they then will get rapidly rebroken, and so they'll be broken to small sizes quickly. But if they're still a little bit too big, then you're back to the surface mechanisms. So the SAG mill is juggling between two different sets of mechanisms, the body breakage from the incremental damage, and if you can't do that, then you'll end up with critical sizes you can't break. But then you've got your dominant mechanism for size reduction is the surface loss, and most of the energy dissipation in the SAG mill is from the surface loss mechanisms. But if your incremental damage and body breakage isn't working, you'll never break the big particles and get them to move down into the smaller size ranges. Okay, so this is an example in a Loveday mill, which is a 1.2 meter pilot mill. The spheres, blue spheres here are balls, so steel balls with high density. These are rocks with different aspect ratios and all fairly blocky. And when this simulation runs, this has the chipping, rounding, and abrasion. So all the three surface loss mechanisms are operating. Now you won't really be able to see any of the size changes because each event just chips off a little bit, and so it's a little bit too small to be visually seen. But we are colouring the particles by their shape factor, and so when they're very angular, it's up at 3.5, and as they're spherical, it goes to 2. And so you'll be able to see the size change and the shape change usually with the colour, even if you can't see the specific events that are leading to the loss. So the surface loss mechanisms are all the accumulation of very large numbers of hundreds or thousands of little impact events, each of which takes a little bit off a corner or an edge, and then progressively leads them to become rounder, as well as sort of grinding down to become smaller. Now, if we had the incremental breakage mechanism switched on here, those particles are now small enough that the energy delivered to them is big enough that those particles could then break. This example is just showing the surface loss mechanisms. Okay, so now we'll jump over to a few crusher examples. So the first one's a jaw crusher. So this is, as usual, using the particle replacement model I described. It's a compression crusher, so the determination of breakage will be done by the particle, the stress on the particle. As usual, the progeny is determined by the T10 model, and again, particle shape is critical. And as with everything we model now, there's certain quadrics. The top size of the feed Q is 600 millimeters, is an industrial scale, and this particle is 600 millimeters across the intermediate axis. So you'll see the particles coming in. The small ones can obviously fall all the way through. The bigger ones are trapped and then compressed by the cyclic compression. There's also a sliding shear component. Once the particles are broken, there's general rearrangement. You can see the very fine material flows very quickly out of the bottom of the jaw crusher. Okay, now next jaw crusher I'll show you is quite a different one. So this is the last example I showed you from the digital human side. So this is a complete model of the human mouth. Essentially, this is where the jaw crusher gets its name from. So you've got two opposing sets of surfaces that cyclically compress and apply stress to the material in between. In this case, we're not showing all the lower part of the mouth. We're not showing the upper part, and we're not showing the teeth. But there's a full set of teeth, and we've got a full biomechanical model here that contains all the details of how all these surfaces move. Now, one of the things that's different to I guess, an industrial jaw crusher is that the tongue plays a critical role here. So it repositions the food and does a whole lot of sorting. So it's a little bit like having an online sorting device, but also preferentially rearranges the larger fragments to improve the re-breakage on the next cycle of the crusher. So the material in this case is an Oreo biscuit. So what that means is you've got two elastic brittle materials with an elastoplastic cream filled material in the middle. This is an SPH model with some DEM components. I won't try to explain too much about what that means, but basically this is using an SPH elastic brittle model prediction, and it's doing a first principles prediction of breakage. Unlike the DEM model, where we're using sort of offline empirical models to tell us what the progeny distribution is, how the breakage occurs. Here the breakage is being predicted from first principles, and so we can then use that for much more complex shapes, both for the feed material, but also the shapes of the progeny are much more complex. I'll just show you a few cycles of the jaw crusher working. So you see the tongue moves over and holds the food in place. There's a cheek on the outside holding it in place on the left. So you get primary breakage. The elastoplastic cream is sticky and sticks some of the pieces together. So the tongue is pushing the largest fragment back over the teeth, trying to position it for the second bite coming down. Human jaw crusher has vertical movement, but also has lateral side-to-side movement as well. So we can make quite complex breakage predictions and size distributions, and lots of secondary physics here which I'll make. Okay, so the last of the crushers I'll look at is a vertical shaft impactor, so high capacity impact-based crusher. So essentially trade feed from a hopper at 400 kilograms a second, rotation rate of 750 RPM, 5 meter diameter crusher chamber, rotor is 1.2 meters, 3 shears on the rotor, feed size is 20 to 70 millimeters. Here's the steady state prediction, so it takes a while to get to steady state. You can see coming down the center here, you've got the choke feed from the hopper. Particles move onto the rotor. You can see they are picked up by the shoes, high-speed jets that are thrown out towards the anvils. You also see that the environment's relatively dense. It's not at all a dilute flow, so there's significant collisions between the outgoing fast-moving particles and the sea of relatively slow-moving fragments from all the previous events, and so there's a lot of secondary breakage goes on. So I'll show a couple of other views looking from the top with half the charge section, so you can see very clearly the flow into and along the rotors, and then the bands of high-speed material flying into the rotors. This last one's a front-on view, gives you a reasonable idea of the density of the flow and all of the material that's particularly trapped above the anvils and very slow moving. So there's something of that material has quite a long residence time. There's a lot of material that's actually essentially trapped down at the side of the rotor and back of the anvils. Okay, so this is a snapshot that shows the particles accelerating outwards. You can see the 3 bands of high-speed material, and you can see a lot of the high-speed fragments from the previous breakage events that are rebounding off the anvils. The next picture, that'll show all the breakage events that have occurred in the last 0.05 of a second. So you can see there's quite a bit of breakage actually occurs on the rotor. There's a large amount of breakage that occurs a fixed band as it moves through, because that's all the collisions between that fast-moving band and all of the resonant material that's floating around in the background. And then you've got high-speed breakage from particles that execute the anvils. So you've got 3 different identifiable components to the breakage that are going on. The interaction of the outgoing streams with the background image, secondary breakage. You can't just look at single particle trajectories and superimpose it, because there's a lot of secondary breakage. Just to give you an idea, there's about 225,000 breakage events per second going on here. There's simulations which think about 20 seconds to get this statement of good data, so about 4.5 million breakage events with up to several hundred progeny in some events. From that, then you get predictions of power drawing and more things like the model for operation. This is then a full prediction of size distribution. So the blue, green here is the feed. Red is what's in the machine, which is a combination of feed and the product that's going to come out. And the blue is the product that's measured at the bottom. One thing that's very important with the way our model's constructed is that we have information on the resolved fragments. So there's always a size that you are prepared to resolve down into the DEM. In this case, it's 4 millimeters. So that's here. But we have all of the information about the finer progeny, and we can use that, get that through the machine, and then predict the fine progeny part of the distribution as well. We're ignoring the sense of getting further secondary breakage of those by hitting things, but very, very small particles don't tend to have a lot of such collisions. So the way we're doing the prediction of the unresolved section actually it's what that means is that we can predict from the full feed size down to, in this case, 200 microns, so we get a full size distribution. And that same type of prediction is what's going to be happening with the SAG model. Okay, so grinding, I'm only going to talk about the complete SAG mill model because it's a complicated model these days. So this is a sort of a structure diagram to show the components and how they fit together. And it's interesting to see what the pieces in published. Most of them, the latest one, it's a current paper I showed this at Comminution last year, and I naturally haven't written the paper yet, so I'm not sure what to get on it. The core of the method is, of course, the DEM method using non-round particles. That's then fully two-way coupled to the SVH method set up to model viscosity fluids. Full two-way coupling between those components. DEM is then connected to the breakage model as it was to the crushers. So all of the dissolved DEM particles that come down here, we're identifying whether they should break and when they should break, and then this is all the 5 breakage mechanisms. So single particle breakage, incremental breakage, and the 3 surface mass loss mechanisms. So all 3 of those are occurring. So we're continuously modifying the size, distribution, mass of material in the DEM model. Coarse fragments from the breakage are always returned back to the DEM model. The fine fragments that are small within the resolved limit taken out of the DEM model and put into the SVH model. So SVH particle represents a volume of fluid, but it also carries the small, fine rock fragments that are in that region. They join the fluid to make a slurry. So we have the SVH particles represent the volume of fluid, and its solids loading is changing with time. So the DEM breakage model is supplying the fine solids into the model for the slurry. Slurry rheology model that says viscosity varies as a function of the solids loading at each point. So every SVH particle has its own for how much solids it's got and what that solids size distribution is. SVH particle can have its own. We also need to worry about fine particle diffusion, which is real dispersion. So if you have a granular material and you shear it, so if there's a lot of fine material on one side and not on the other, the shearing of that granular material will cause dispersion of the fine material. So there's a net migration of fine particles across the granular material, across the slurry in response to dispersive forces, but it basically behaves like a diffusion. So we can model that as a particle diffusion for the fines within the slurry. The final component that we've got here is a fine particle grinding model, and I'll talk about that in a few slides about it. Okay, so what we've used to do the fine grinding predictions of population balance model, instead of using a single population balance model at the system level, what we've done is embedded a particle population balance model in every single SVH particle. So let's say there's 1 million SPH particles in the fluid, every one of those has its own embedded population balance model, does its own calculations for the effect of the gradient at that location. Now, there's a number of issues that are normally identified with population balance models when trying to use them on mills, and a lot of those relate to non-first order grinding kinetics, but mostly that relates to very coarse particles. Other problems that cause us to not think this is the optimal way for us to go is that when you do the population balance model external to the particle-based simulation, you're essentially making assumptions like the charge is fully mixed or sections of charge are fully mixed. So making assumptions that all parts of the charge sample, all parts of the phase space in terms of available states that are available, but in reality, a lot of the particles are actually trapped in sub-regions and they only sample very specific subsets of the overall dynamics, and that affects the breakage kinetics in those regions. There's been quite a few people who have formulated energy-based population balance models, and those are suitable for combining with DEM, so we use some of those. It's noted, of course, that quite a few people have used these in the past, and we've seen us done a lot of work in combining these data. The key difference here is that we're putting the inside the okay, so in the complete particle scale model, we have an independent population balance model with every SPH particle. Local grinding prediction means that there are no assumptions on sort of global mixing or what's happening in the phase space. Because each SPH particle is only a very small local calculation with a very small body. Coarse particles are being explicitly resolved in the DEM. The breakage is being done in the DEM, so there are no coarse particles in the population balance model, so we don't have problems with the non-first order grinding kinetics. The population balance model also is sort of generally known to work better for fine size fractions. So where applying the population balance model, its absolute strengths are not using it, but it's more difficult to use it essentially to do that. The form that we're using is from Comminution 2014. It doesn't really matter which one you use, as long as it's an energy-based one, and you can swap between those if there's good reason. So selection and functions are also a matter of choice. The important thing here is that we're using the energy dissipation at every point in the DEM model, so we know the energy dissipation from the dissolved solids from the rock and from the walls. That energy dissipation rate is the energy source that is used in the population balance model for particles. So every SPH particle is not only doing the local calculation, but it's using it with an energy input that is specific to that particular location at that specific time. I won't go through the equations, but these are sort of standard population balance equations just to look like. And we use essentially pretty standard selection breakage functions. So the model's not dependent on the specific choices. It doesn't like these particular something else on these things anyway. We've also got a slurry model which relating the viscosity to C2 as the solids loading. So there's the amount of solids in the final size fraction. So there's a strong disproportionate effect of the smallest lines on the viscosity. So if you load very small size classes, the viscosity goes up much faster than just from the solids loading. All of these bits sit in that slurry grinding model that was in the upper part of that phase diagram. Just a little bit of detail like into these. So we've got size distribution for balls, size distribution for box, shape, distributions. Fine slurry sizes going from 5 size fractions in the balance model, so that the blocks as they enter the slow then will okay, so that's more slides than I normally show without videos. So now we have had some videos. So this is the Hardinge mill that Rob and I have been working on for years or whatever. And obviously, updating and expanding the computational framework, but the model itself is pretty much the way it was 20 years ago. So what we've got here is about 30% solid, 39% solids loading. There's about 160 litres of water initially in the mill. Solids here slowly is shown by slowly. No particular surprises here. Everybody's seen lots of models in a central slice. So the slice for a couple of models is fairly similar. The differences where it becomes a bit more interesting is what's the slurry distribution look like. So what the slurry turns over quite quickly. It's got relatively high permeability through the charge that turns over the surface, and then there's a layer that's sort of very close to the wall that separate. So you've got some slowly distributed cataract extreme. This is looking at an axial view. So now we've got a chute here slowly going onto the chute. We've also got blocks below it as well. Great whole chamber. So here we're looking at the axial transport of solids and liquids through the full mill. One of the things you can see is that the flow is really very complicated. It's a significant flow off these in-wall lifters, and they come down into the middle of the line. It's actually very poor mixing the transport across the central line of the so you get reasonably quick mixing with cycles. That flow basically throws stuff into the middle and circulates back into the recirculation zone on its side. But it's quite difficult to slow across that mid-plane. But the complex sort of lifter geometries then slowly here produces really quite complex axial flow patterns. So you can see here that there's fluid going sometimes one way, sometimes the other. There's no simple flow pattern between the slowly edge of approaching the toe position, which reflects the very large variability of all the conditions. But we're also predicting the flow through the grates, the flow then up and down. This is a steady state of what's in the pulp chamber. We've shown this type of picture before, but it was for very early stages. What we find is that when we start the mill off with water in there, there's quite a large surge of water into the pulp chamber to start with, and then that declines over time. This is once we've got to steady state. So the brown pebbles that have got through the ground slots, and is the slurry that's going through. The slurry behavior is extremely complex. We're still trying to understand exactly where and how the slurry goes through the grate panels. There's no mechanism built into this design that stops backflow from the pulp chamber back into the grinding chamber. So we can see strong backflow into the grinding chamber here. We can see flow into the pulp chamber at a number of different locations, and we can also see when we've got large deposits like this, the pressure mechanism for some slurry back through the grate. So it's really quite a complex flow between the grinding chamber and the pulp chamber. We're still trying to figure out how to do the analysis of that. So one of the challenges we have is Now, on this mill, it's a very geometrically very complex mill. There's a lot of things happening in a lot of places, and we're looking at slurry, all different size fractions of slurry, all different size fractions in the rocks, the breakage, they're all very spatially, and we also don't know what the steady state conditions for this mill are. So there's an enormous amount of data and an enormous amount of complexity geometrically from a process perspective. So the challenge we have here is what data to try and collect in order to show what's going on, to try to just understand what all the detail of particle and fluid mechanics are going on. Having said that, here's the steady state flow. The frame rate is a bit on the coarse side, so it's a bit jumpy. But one of the things that's interesting is the solids naturally all settled to the back of the lifters over here, and that throws over there in dirt. So you see the solids all landed on the slurry. The solids here are typically only sort of 6-7 millimeters. The slurry's got a reasonable viscosity, so it actually takes a bit of time for the particles to settle back through the fluid. And the time available for that before you go up lifters and start cycling beams only sort of order of second. So you don't have very long for the solids to resettle through the slurry. So you've got quite a complex dynamic balance going on here as the solids respond to gravity, try to sink through here, but the whole thing moves up quickly, so you can see the surface layers there. Here it's starting to make some progress, and now it's stratified. So even where the solids are within the fault chain, it's very complex distribution, heavily dependent on the phase of This is now looking at the, just one slide, looking at the importance of damage accumulation. One of the reasons why we've done this for much longer time. So this is a picture at about 1 second. There's only been a sort of modest amount of damage so far. The circles out with the crusher are showing where the breakage events occur. What's interesting here is people have been looking for a very long time with the what's the rate of energy dissipation in different parts of the charge, and the energy dissipation reported as being maximal in this region. One of the things that's interesting is that the intensity distribution of breakage events coming from incremental breakage is strongly emulating that energy dissipation distribution. What would you expect in this case? Where the damage accumulation is particularly important. This is after one revolution, so you can see all the particles are circulated around, and a lot of the particularly bigger particles have accumulated some damage on the previous pass. So here you'll see everything that's coming in is covered by the total damage energy that absorbed. So these particles have not had any collision, so they will have no damage energy. But after a full revolution, you'll see that the particles that are in the stream, particularly the larger ones, have accumulated quite a bit of energy. Maximum here is getting towards the level that we cause breaking. So things that are there are sort of not far away. You don't need to be too many times to break. And so you'll see there's a bit of a change in the distribution, and particularly getting a lot more breakage of the toe region as essentially to also rocks that have accumulated some damage already when they hit the liner, or more importantly, some of the rocks have all bounced back and hit incoming particles. That's going to be additional breakage of the coarse particles. That breakage of coarse particles in and above that toe region is to understand the breakage of the coarse size fractions and the stream of the mass from those coarse size fractions into smaller ones, which are predominantly dealt with by the surface attrition. Now, in this particular model, we can accelerate the rate of. Sorry?
I'm sorry to interrupt. We are running out of time. Maybe you can. go to
So,
conclude, and then we can have a couple of questions after that.
right, so this one's the breakage rate's been accelerated by a factor of 6. So this is at 42 seconds essentially. So that's equivalent to a bit over 4 minutes of grinding. So a significant fraction of the real time to grind rocks. And what we're finding on for this particular set of rocks is that we've broken a significant fraction of those rocks. We've used the E0 in this case is constant of size. There's no size dependence in this particular one. And we're getting some very interesting effects. You can see that we're getting a strong forcing of the charge. So we've got perhaps only 2/3 the number of particles, but about 10% more mass. So the fill level is actually going up a little bit. It's not steady state. But we've got a significant amount of green to light blue, particularly in the outer region. So this inner region, this core, is made up of the fine dark blue particles. So basically, because the E0 is the same for those coarse and large particles or small particles, we're preferentially breaking all of the dark blue particles, and so we're getting a build up of the intermediate sizes. So we're getting a significant change in size distribution. That's one of the strengths of where the model is now, is that we're with the breakage mechanisms now built into the model. We can now predict the evolution of the resident size distribution and what the consequences are for that for the This one's just a slide showing discharge rates. You can see we've got very high discharge rates all along, and by about 25 seconds, it's down to about 0.4 per second. The feed rate's about 1. So 2/3 of the slow is not coming out, it's actually building up in the middle. That's most likely because the solids load is still going up, and the grinding is causing viscosity to go up. Okay, so very quickly now, this is just looking at the slurry phase grinding. So this is looking at the overall viscosity, which is a function of the solids loading. So all the coarse particles are breaking, the fine particles are grinding. So viscosity is a measure of the distribution of those solids. You see in particular, we see this all the time, that we get generally a preferential band of high viscosity in that region, but the breakage is high, and a reduced viscosity in the core. This is just the viscosity at very long time, so I can't stop that one.
Thank you, Paul.
Chairman gave me the speed up, and when I finished, that I had achieved.
Yes. Thank you very much for the very interesting presentation. Well, I think we can have time here for a couple of questions. Maybe you can open your mic and raise your hand. Does anyone has a question?
I'd be satisfied or desperate to leave.
I do, of course, have numbers of questions in my head, but I thought to give other people a chance. So I think, Paul, the tour de force is, as usual.
You can always call me back another time and we can talk about it. We don't have to talk once a year.
Yeah, that we always avoid each other in Australia. Yeah. But it's really fascinating, that journey of putting together, as you showed, the incremental parts of the system to gradually build up the full, as full a picture as we know. Incredibly challenging and interesting problem, as I kind of introduced it, and that you got down to the level of local population balance model to solve the fine end of the system. And really, I think that is a pathway which you had the virtual comminution model concept of building understanding to then design the future. I guess the question is, have you applied this methodology to any designed machines, or someone's crackpot idea or good idea of what a new machine might be, and then you could test in advance whether the concept is useful, viable, going to be any better. Have you managed to do any of that yet?
Yes, we're at a number that's well above 2 and less than a handful. The obstacles to sort of moving forward from that sort of some run into problems with manufacturers who have their own agendas. Some to test them, you've got to build one, and then that takes a significant amount of time and money, and I can't talk about any of those. There's a few that are sort of still we've looked at it on the computer, but we haven't really tried to take them into the real world yet. So yes, we're probably my focus here on is much less than working with existing OEMs on the existing machines, and much more on using the tools on virtual machines that don't exist yet to try and sort of significantly increase the rate that we can produce new machines and improve them. We can do the modeling in say 3 or 6 months, and then we've still got to wait a couple of years for somebody to build and run one and test it. That bit we can't speed that bit up. We can take out a lot of the incremental sizes, so you don't go through laboratory through several pilot. We can go straight to full operational size, but building and testing at operational size is that's a fairly, as you know, a fairly serious commitment.
And it's an industry thing of getting confidence in the process to take that big hop leap. To me, that's where the value lies. Yeah.
Yes. So and beyond that, everything I could say beyond that is confidential. But we're not using it that way. That's the bottom line to what you wanted to know.
Yeah, you are pursuing it, which is good to hear.
Yeah, just have to. We're going to have to wait a bit longer before you hear anything. Where hopefully that's measured in a small number of years, not decades. But anyway.
Hope so. Looking forward to it.
Yep.
Any other questions?
Okay, maybe you've stunned them all, Paul. So I can just close with a thank you, unless Olga, you're leaping in with a last minute one.
Yeah, this took a while to switch on. Paul, first of all, thanks for a lot for the presentation. Looking at your final slides on the egg mill or sag mill, on the particle motion there, I was astonished how high you lifted the particles before they dropped again. So I think you have been way beyond 75% critical speed. I would assume you modeled some 80% or something. I was surprised about the throwing of the particles.
Yeah, that's standard sort of hard hinge operating conditions. So I think from memory, it's 76% critical. It's a 39% solids load, which is what they used to use 100 years ago when Rob got the data. But now people would tend to use more 30. So we're thinking about whether we should bring the fill level down. That has a strong effect on the height trajectory. So if you're running essentially nearly 40% at 76, that's what you get, particularly on a small mill.
Okay, thanks.
Well, thank you very much, Paul. Really elucidating, interesting as usual. Really enjoyed it, and thanks everyone for joining us. Be up in a month's time again.
Yeah.
Thank you, Paul. Thank you, everyone.
Yeah. Thanks a
Cheers,
lot.
everyone.
Cheers.